Antimatter has a mind-boggling concept that has enthralled sci-fi enthusiasts, especially those who love Star Trek and other space adventure movies. Antimatter is the intriguing counterpart of regular matter, known for its incredible energy and volatility. In sci-fi, it powers warp engines and can obliterate spaceships with well-placed torpedoes. But beyond fiction, antimatter is a real thing. Though quite rare, this rarity might be a blessing given its immense power. However, if we could harness it on a large scale, it could bring about revolutionary changes in our world. Let's take a moment to think about the origins of the universe. After the Big Bang, the early cosmos had equal amounts of matter and antimatter created alongside energy. But here's the curious thing. As we look around, we see way more matter than antimatter. The enigma of antimatter goes even deeper. Surprisingly, particles and their antiparticles behave in the same way. If matter and antimatter were created in precisely equal percentages, they should have annihilated each other out of existence. As matter and antimatter got created and destroyed together, one would think the universe consists solely of leftover energy. This leads to a profound question. Why does matter overrule antimatter in our cosmic story? What caused this cosmic imbalance? Solving the puzzle of why there's more matter than antimatter is one of the biggest issues in physics. Particles of antimatter have the same mass as regular matter particles, but have opposite characteristics, like an electric charge. For example, the antiparticle of a negatively charged electron is a positively charged electron. Some particles, like neutrons, have no electrical charge and intriguingly exist as their antimatter counterparts. Scientists are still working to figure out if neutrinos, these mysterious tiny particles without electric charge, also have their unique antiparticles. The study of antimatter is a thrilling journey of discovery, with potential implications for our understanding of the universe and technological advancements. While it may seem like the stuff of science fiction, the real-world applications of antimatter hold great promise. In the realm of human scientific achievements, we have witnessed the creation of antimatter particles through ultra-high-speed collisions in massive particle accelerators, like the Large Hadron Collider. At CERN, the European Organization for Nuclear Research, scientists have managed to create anti-hydrogen, the antimatter counterpart of hydrogen, and even anti-helium, which is essentially helium's twin. These breakthroughs represent significant milestones in studying antimatter. In the vast universe, we sometimes find natural antiparticles created in occasional bursts. However, when antimatter meets regular matter, they eliminate each other, releasing enormous energy and leaving only a brief existence for antimatter in our matter-dominated universe. One fascinating theory suggests that during the early universe, a tiny asymmetry between matter and antimatter was established since matter was produced more than antimatter, leading to an abundance of matter. This seemingly small difference played a crucial role in shaping the cosmos, allowing stars, galaxies, and everything we see on Earth to form. According to Space.com, this disparity was so minute that less than 1 of 1 billion particles survived annihilation to become the matter we know today. The elusive neutrino emerges as a potential key to unraveling the cosmic mystery. Being a ghostly particle with limited interactions with other matter, the neutrino could have the unique property of existing as its antiparticle. According to this theory, a small number of neutrinos in the early universe might have undergone changes from antimatter to matter, which caused a slight but crucial imbalance that led to the dominance of matter. Scientists have conducted numerous experiments to ascertain whether neutrinos indeed have this unique antiparticle, but so far, the results remain inconclusive, adding to the intrigue surrounding this captivating particle. The world of antimatter changed in 1928, when physicist Paul Dirac made a remarkable prediction. While working on an equation for relativistic electrons, he found two solutions. Electrons had either positive or negative charges. He cleverly interpreted the negative energy solution as a new kind of particle with the opposite charge, which he called the positron. Dirac then proposed that every particle had an antiparticle, having almost the same mass but being oppositely charged. Interestingly, positrons are naturally produced in radioactive processes, such as the decay of potassium-40 found in the bananas that we eat every day, which emits these tiny particles every 75 minutes. Positrons collide with electrons in matter, creating a spark of light. Additionally, medical technology now uses antimatter in PET scanners, benefiting various medical applications. The existence of antimatter received its first experimental evidence in 1932, when Carl Anderson observed cosmic rays in a magnetic field and cloud chamber. He verified that although positrons twisted away from the electrons in the magnetic field, they had the same mass as electrons. Emilio Segre and Owen Chamberlain made history in 1955, when they used Berkeley's Bevatron accelerator to produce the first antiprotons. They also noticed that protons were destroyed by antiprotons, creating pions. To create antimatter, scientists need high-energy collisions like CERN's Large Hadron Collider that can create mass from energy, following Einstein's famous equation E=mc². By smashing protons together at nearly the speed of light, they generate a rain of antiparticles and particles. The majority of the collision energy is lost as heat or radiation, and only a little amount transforms into antimatter. As a result, making antimatter is still a difficult and expensive procedure. Recent particle physics experiments have shown that the laws governing nature treat matter and antimatter differently. This disparity has piqued the interest of physicists worldwide, leading them to search for the underlying reasons. It's believed that some unknown entity might have intervened during the early universe, causing spinning particles to decay mainly as matter rather than antimatter. To illustrate this phenomenon with an analogy, imagine a spinning coin on a table. While it spins, it can't be labeled as either heads or tails. However, once it stops spinning, its fate is determined. The probability of a coin landing on heads or tails is 50-50. If a couple of coins are spun identically, half will probably land on heads and half will land on tails. Similarly, in the early universe, the spinning particles should have decayed to matter and antimatter equally. But imagine a peculiar marble rolling amidst the spinning coins, making every coin it touches land on a head. Such an intrusion would change the whole system, resulting in an imbalance with more heads than tails. Likewise, some mysterious mechanism might have interfered with the spinning particles, leading the majority of them to decay as matter instead of antimatter. Scientists hope to uncover clues about this process by studying the major and minor differences and changes in the decay of matter and antimatter created during high-energy proton collisions at CERN. These investigations could help scientists understand why our universe is mostly made of matter. To understand the fundamental foundational blocks of matter and antimatter, we need to understand the elementary particles known as quarks and leptons. Antimatter carries negative lepton numbers, while matter carries positively charged ones. Particle physics introduces us to the family of quarks consisting of 6 unique members: the up and down, the charm and straight, and the top and bottom. Complementing these quarks and the leptons, another group of 6, which includes 3 intriguing neutrinos and the moon, electron and tau. Each of these 12 particles has a twin in the realm of antimatter, differing solely in their electrical charge, a perfect reflection of their normal counterparts in principle. Fascinating experiments have illuminated intriguing deviations from the concept of perfect symmetry between matter and antimatter. Among neutral mesons, a remarkable phenomenon emerges as spontaneous transformations into their corresponding antimesons and antimesons into mesons. During this change, quarks can evolve into antiquarks, leading to intriguing outcomes. Experiments have demonstrated that this transformation occurs with a greater propensity in one direction compared to the opposite. resulting in a gradual preference for the production of matter over antimatter as time progresses. This asymmetry has been observed predominantly in particles housing bottom and strange quarks, a monumental revelation in the world of particle physics. The very first detection of the strange particle asymmetry in 1964 was of great significance because theorists got to discover the last 3 remaining quarks. This breakthrough eventually culminated in the discovery of asymmetry in bottom particles in 2001, solidifying the framework for the 6-quark model. These groundbreaking discoveries have earned distinguished scientists Nobel Prizes for their exceptional contributions to our understanding of the intricate subatomic realm. Researchers have been studying the electric charges of quarks. They found that the bottom and strange quarks are negatively charged, while the charm quark is the only positively charged one. Scientists have been trying to determine if charm quarks can create particles with matter-antimatter asymmetry, although any such effect is expected to be very tiny and hard to detect. Recently, the LHCb experiment at the Large Hadron Collider achieved a groundbreaking discovery. They observed matter-antimatter asymmetry in particles called D-mesons, which are made of charm quarks. This achievement was possible due to the large number of charm particles directly produced in the collisions, a feat accomplished a decade ago. The significance of this observation is highlighted by the incredibly tiny chance of it being a random occurrence, only 50 in a billion. If this asymmetry comes from a different source than what causes asymmetries in bottom quarks and strange quarks, it opens up new possibilities for explaining the total asymmetry in the early universe. This is important because the known cases of asymmetry alone cannot fully account for the abundance of matter in the universe. Although the discovery of charm quark asymmetry is a crucial piece of the puzzle, it might not be sufficient on its own to fully comprehend the balance of matter and antimatter in the universe. Nonetheless, it represents a significant step forward in understanding the interactions of fundamental particles, bringing us closer to unraveling the mysteries of the universe. The entire periodic table probably has antimatter counterparts such as anti-hydrogen, anti-carbon, anti-nitrogen, and even anti-oxygen. Taking this idea further, there could be anti-uranium, anti-iron, and anti-gold compounds, giving rise to antimatter compounds like anti-water or maybe anti-proteins. The theoretical side of this concept is less challenging since the laws of physics don't forbid the existence of antimatter versions of every element in the periodic table. However, making and containing antimatter is, in reality, extremely cost-intensive. So far, scientists have only managed to create a small number of anti-hydrogen atoms and have reached as far as an anti-helium nucleus in generating antimatter elements. While the idea of antimatter counterparts to all elements is exciting, the obstacles in production and containment show how complex it is to work with antimatter. And that brings us to the end of this video. If you like this video, click on the screen to watch other videos like this one. Don't forget to like, subscribe, and click on the notification bell to get notified when we post a new video.